Hello there, and welcome to the Sleepy Library. Tonight, we embark on a gentle journey through the cosmos, exploring one of humanity's most remarkable achievements, how spacecraft travel through the vast emptiness of space. Let yourself settle in, breathe slowly, and allow your mind to wander among the stars as we uncover the peaceful science behind these extraordinary machines. Space is not like anything we experience on Earth. There is no air to breathe, no wind to feel, no sound to hear. It is a realm of profound silence and endless darkness, punctuated only by the distant glow of stars. Yet, through this emptiness, spacecraft glide with grace and purpose, carrying our instruments, our curiosity, and sometimes even our astronauts to destinations millions of miles away. How do these vessels move through nothingness? What invisible forces guide them on their journeys? Tonight, we will explore these questions together in the most soothing way possible. Imagine yourself floating in the deepest ocean, so deep that no light penetrates from above. Now imagine that ocean has no water, no substance at all. That is space. It is emptiness on a scale our minds struggle to comprehend. Between Earth and the Moon, a distance of about 384,000 kilometers, there is almost nothing. A few stray atoms of hydrogen, perhaps, the occasional mote of dust, but for the most part, it is vacuum. Between planets, the emptiness is even more profound. Between stars, it becomes almost absolute. And yet, this emptiness is not truly empty. It is filled with invisible forces, subtle influences that shape the paths of everything within it. Gravity reaches across millions of kilometers, pulling planets around the sun, moons around planets, and spacecraft along carefully calculated trajectories. Magnetic fields stretch through space, created by spinning cores of iron deep within planets. Solar wind, a stream of charged particles flowing from the sun, fills our solar system with a tenuous plasma. Cosmic rays, high-energy particles from distant exploded stars, zip through space at nearly the speed of light. Into this strange realm, humanity sends its mechanical ambassadors. Some are small, no larger than a toaster oven, packed with miniaturized electronics and instruments. Others are massive, weighing thousands of kilograms, bristling with antennas and solar panels and scientific equipment. Some stay close to Earth, circling our planet in low orbit, completing a full revolution every 90 minutes. Others venture to the very edge of our solar system and beyond, spending decades in transit, crossing billions of kilometers to reach their destinations. Each spacecraft is a miracle of engineering, a carefully orchestrated symphony of systems working together in perfect harmony. They must survive the violence of launch, where they are shaken with incredible force and subjected to accelerations that would crush a human body. They must endure the extremes of temperature in space, where one side might bake in unfiltered sunlight, while the other freezes in the shadow. They must function for years, sometimes decades, without maintenance or repair, every component performing flawlessly, because there is no second chance in the void. The humans who design these spacecraft must think differently than engineers who design machines for Earth. On our planet, if something breaks, you can fix it. If you forget something, you can add it later. If conditions change, you can adapt. But in space, what you launch is what you have. Every bolt, every wire, every line of computer code must be perfect. Every contingency must be anticipated. Every backup system must be reliable. The spacecraft must be autonomous, capable of making decisions on its own when communication with Earth is delayed or interrupted. Consider the Voyager spacecraft, Those remarkable twins launched in 1977. They were built to last 5 years and explore Jupiter and Saturn. Yet here we are, nearly 50 years later, and they are still functioning, still sending back data from the space between stars, farther from Earth than any human-made object has ever traveled. They have survived impacts from micrometeorites, fluctuations in temperature, the gradual decay of their radioactive power sources, and the accumulated damage from cosmic radiation. Their computers have less processing power than a modern digital watch, yet they continue to navigate, to observe, to transmit across more than 20 billion kilometers of space. This is the nature of spacecraft. They are built not just to work, but to endure. They are testaments to human ingenuity, to our ability to imagine something that has never existed, and then bring it into reality through careful thought and precise construction. And the principles by which they operate, the laws of physics they obey, are things of elegant simplicity, universal truths that apply everywhere in the cosmos. The story of spacecraft travel begins not with complex machinery, but with a simple principle discovered centuries ago by a man named Isaac Newton. He understood something fundamental about the universe. For every action, there is an equal and opposite reaction. When you push against a wall, the wall pushes back against you with the same force. When a bird flaps its wings downward, the air pushes the bird upward. This same principle allows spacecraft to move through the vacuum of space, even where there is nothing to push against. Newton's insight came from observing the world around him and thinking deeply about motion. Before Newton, people believed that objects naturally came to rest, that motion required a continuous force. If you pushed a cart and then stopped pushing, the cart would slow down and stop. This seemed to suggest that motion needed constant effort. But Newton realized that this was an illusion created by friction. A ball rolling across the ground slows down not because its motion requires force, but because the ground and air resist its movement. In the absence of such resistance, an object in motion would continue moving forever at the same speed and in the same direction. This revelation changed everything. His 3 laws of motion form the foundation of how we understand movement in the universe. These laws are not complicated equations requiring advanced mathematics. They are simple statements, almost poetic in their elegance. Yet they describe everything from the fall of an apple to the orbit of planets to the trajectory of spacecraft across billions of kilometers. The first law tells us that an object at rest stays at rest, and an object in motion stays in motion, unless acted upon by an external force. This is the principle of inertia, the tendency of things to maintain their current state. We might call it the law of laziness. Objects resist changing what they are doing. A book on a table will sit there forever unless something moves it. A hockey puck sliding across ice will continue sliding unless friction or a collision stops it. In space, where friction is absent and gravitational forces are weak over short timescales, inertia dominates. A spacecraft that achieves a certain velocity will maintain that velocity indefinitely, coasting through the void without expending any energy. The second law tells us that force equals mass times acceleration. This mathematical relationship describes how the motion of an object changes when a force is applied. It quantifies what we intuitively understand. Pushing harder makes things speed up faster, and heavy things are harder to accelerate than light things. A large spacecraft requires more force to accelerate than a small one. The same engine will cause a light spacecraft to speed up quickly and a heavy one to accelerate slowly. This is why minimizing mass is so crucial in spacecraft design. Every extra kilogram requires more fuel to accelerate, which itself adds mass, creating a challenging cycle that engineers must carefully navigate. The second law also tells us something profound about mass itself. Mass is not just the amount of stuff an object contains. It is a measure of inertia, a measure of how much an object resists being accelerated. A massive object has more inertia than a light one. It takes more force to change its motion. This connection between mass and inertia is fundamental to how the universe works. The third law, the one most relevant to rocket propulsion, tells us that for every action there is an equal and opposite reaction. This is not just a saying, it is a fundamental principle of nature rooted in the conservation of momentum. Forces always come in pairs. You cannot exert a force on something without that something exerting an equal force back on you. When you step forward off a boat, the boat moves backward. When a gun fires a bullet forward, the gun recoils backward. When a rocket expels hot gases downward, the rocket moves upward. The forces are always equal in magnitude and opposite in direction. Let us dwell on this principle for a moment, for it is truly remarkable. Imagine standing on a perfectly frictionless surface, like ice so smooth that you cannot get any traction. You are stuck, unable to walk forward because walking requires pushing backward against something. Your feet need friction to push against the ground. Without it, you simply slide helplessly. But if you have a bag of rocks, you can throw them away from you, and you will slide in the opposite direction. Each rock you throw will give you a little push. The heavier the rock and the faster you throw it, the more momentum you gain. This is not magic, it is physics, the unavoidable consequence of conservation of momentum. This is exactly what a rocket does, except instead of throwing rocks, it throws molecules of gas. And instead of throwing them one at a time, it expels billions upon billions of them continuously at tremendous speed. The rocket engine becomes a machine for converting chemical energy stored in fuel into kinetic energy of motion, transforming the momentum of gases into the momentum of the spacecraft. It is elegant in its simplicity and powerful in its execution. Momentum itself is a beautiful concept. It is the product of mass and velocity, a measure of how much oomph a moving object has. A freight train moving slowly has enormous momentum because of its great mass. A bullet moving rapidly has significant momentum despite its small mass. What makes momentum special is that it is conserved. In any closed system, the total momentum before an event must equal the total momentum after. This law is absolute, universal, unbreakable. When a rocket sits on a launch pad before ignition, its momentum is zero. The rocket and all its fuel are stationary. The total momentum of the system is zero. When the engines fire, fuel begins to burn and hot gases rush out of the nozzles at perhaps 3 kilometers per second. These gases now have momentum, lots of it, in the downward direction. But the total momentum must still be zero. So the rocket must gain an equal amount of momentum in the opposite direction, upward. As more and more gas is expelled, the rocket accelerates upward faster and faster. This might seem to violate common sense. After all, the rocket is becoming lighter as it burns fuel, and lighter objects should be easier to accelerate. And indeed, they are. As the rocket rises and fuel is consumed, the mass decreases, while the engine produces the same thrust. So the acceleration increases. This is why rockets accelerate gradually at first, and then more rapidly as the flight continues. The engines provide constant force, but as mass decreases, acceleration increases, according to Newton's second law. There is a famous equation, the Tsiolkovsky rocket equation, named after a Russian scientist who worked out the mathematics of spaceflight before rockets even existed. This equation describes how much velocity a rocket can gain based on the ratio of its full mass to its empty mass and the velocity of its exhaust. The equation reveals a troubling truth. To achieve high velocities, you need either extremely fast exhaust or extremely low final mass compared to initial mass. In practice, this means that most of a rocket's mass must be fuel. Consider the Saturn V rocket that sent astronauts to the moon. It stood 110 meters tall and weighed 2.8 million kilograms fully fueled. Of that enormous mass, only about 45,000 kilograms was the Apollo spacecraft and its crew. The rest, more than 98%, was the rocket structure and fuel. All of that fuel was burned in just 11 minutes to achieve the velocity needed to reach the moon. This is the tyranny of the rocket equation. Going faster requires more fuel, but more fuel adds more mass, which requires even more fuel to accelerate. This is why staging was invented. Instead of trying to carry one giant engine and fuel tank all the way to space, rockets are built in stages. The first stage burns its fuel and then separates, falling away. The second stage, now lighter because it no longer has to carry the empty first stage, continues accelerating. On very large rockets, there might be 3 or even more stages, each one shedding its empty weight as it completes its job. The Saturn V had 3 stages. The first stage, called the SIC, had 5 enormous F1 engines burning kerosene and liquid oxygen. These engines produced 7.6 million pounds of thrust, enough to lift the massive rocket off the pad and accelerate it through the dense lower atmosphere. After just 2.5 minutes, the first stage had burned through more than 2 million kilograms of propellant and was discarded. The second stage, the S2, took over with 5 J2 engines burning liquid hydrogen and liquid oxygen, a more efficient combination. This stage burned for about 6 minutes before being jettisoned. Finally, the third stage, the S4B, with a single J2 engine, completed the journey to orbit and later reignited to send Apollo toward the moon. Each stage was optimized for its part of the journey. The first stage needed brute strength to overcome gravity and air resistance near the ground. The second stage operated in thinner air at high altitude, where aerodynamic efficiency mattered less and engine efficiency mattered more. The third stage worked in the vacuum of space, where only thrust efficiency mattered. This careful staging allowed the Saturn V to deliver about 4% of its initial mass to lunar trajectory, far more than a single-stage rocket could have achieved. Let us explore the heart of how this happens, inside a rocket engine. Most spacecraft use what are called chemical rocket engines. These engines burn fuel to create hot gases that shoot out through a specially shaped nozzle at the back of the rocket. The fuel consists of 2 main components, a fuel substance and an oxidizer. The oxidizer provides the oxygen needed for combustion, which is necessary because there is no oxygen in space to support burning. The process begins in the combustion chamber, a strong metal cavity where fuel and oxidizer meet. In liquid rocket engines, pumps deliver these propellants from separate tanks. The pumps themselves are marvels of engineering. They must deliver hundreds or thousands of liters of propellant per second while operating at extreme temperatures and pressures. The turbopump on the Space Shuttle's main engines, for example, spun at 37,000 revolutions per minute and developed as much horsepower as 28 locomotives. When the propellants mix in the combustion chamber, they react violently, releasing enormous amounts of energy. The temperature inside can reach 3,000 degrees Celsius or higher, hot enough to melt most metals. The chamber walls must be cooled, often by circulating cold fuel through channels in the chamber walls before it enters the combustion zone. This regenerative cooling serves double duty. It protects the engine from melting and preheats the fuel, improving efficiency. The hot gases produced by combustion want to expand in all directions. The combustion chamber is designed to contain them, with only one escape route: the nozzle. The nozzle is not simply a hole. It is a carefully shaped cone that accelerates the gases to supersonic speeds. The nozzle begins with a narrow throat, the smallest cross-section, where the gas velocity reaches Mach 1, the speed of sound. Beyond the throat, the nozzle expands into a bell or cone shape. As the gases enter this expanding section, they accelerate further, reaching velocities of Mach 10 or higher by the time they exit. This might seem counterintuitive. Normally, when a gas flows through an expanding passage, it slows down. But at supersonic speeds, the physics reverses. In supersonic flow, expansion causes acceleration. The expanding nozzle allows the hot, high-pressure gases to convert their thermal energy and pressure energy into kinetic energy, into directed motion. By the time the exhaust leaves the nozzle, it is moving at perhaps 3 kilometers per second relative to the rocket, carrying with it the momentum that propels the spacecraft forward. The shape of the nozzle is critical. If it is too short, the gases do not fully expand and energy is wasted. If it is too long, it adds unnecessary weight. Engineers must optimize the nozzle for the atmospheric pressure at which the engine will operate. A nozzle designed for sea level has a different shape than one designed for vacuum. This is why some rockets have multiple nozzles or adjustable nozzles that can change shape during flight. Different propellant combinations have different characteristics. The choice depends on many factors: the required thrust, the efficiency needed, the storage requirements, the cost, and the toxicity. Let us explore some of the most common combinations. Kerosene and liquid oxygen is a classic combination. Kerosene, refined petroleum, similar to jet fuel, is dense and relatively easy to handle. Liquid oxygen must be kept at -183 degrees Celsius, cold enough that it will boil away if not properly insulated, but not as difficult to manage as some other cryogenic propellants. This combination provides good thrust and reasonable efficiency. The F1 engines that powered the Saturn V first stage used this propellant pair. The fuel burned with a distinctive orange flame, bright enough to turn night into day for miles around the launch pad. Liquid hydrogen and liquid oxygen is more efficient but more challenging. Hydrogen is the lightest element, which means that for a given energy release, it achieves higher exhaust velocity. The J2 engines on the Saturn V upper stages used this combination. But liquid hydrogen is extraordinarily cold, existing as a liquid only below -253 degrees Celsius. It is also the least dense liquid, meaning you need very large tanks to hold a useful amount. And hydrogen molecules are so small they can leak through tiny imperfections in seals and welds. Despite these challenges, liquid hydrogen, oxygen, remains the gold standard for upper stage engines, where efficiency matters most. Hypergolic propellants are fascinating because they ignite spontaneously when they contact each other, without needing a spark or flame. The most common hypergolic pair is hydrazine derivatives and nitrogen tetroxide. These liquids are stored at room temperature, which simplifies the engineering considerably. No cryogenic insulation, no boil-off losses, no concerns about the propellants warming up during a long countdown. This reliability makes hypergolics popular for spacecraft engines that need to restart in space, sometimes years after launch. The Apollo Service Module engine, which performed the critical maneuvers to enter and exit lunar orbit, used hypergolic propellants. The downside of hypergolics is toxicity. Hydrazine and nitrogen tetroxide are extremely poisonous and corrosive. Handling them requires protective suits and careful procedures. Spills can be catastrophic. Yet, their reliability and storability make them invaluable for applications where engine restart capability is essential. Many satellite thrusters use hypergolic propellants because the engine can sit dormant for months or years and then fire instantly when needed. Solid rocket engines work on an entirely different principle. In these engines, the fuel and oxidizer are mixed together into a rubbery solid substance called propellant grain. This grain is cast or molded into the shape of a hollow cylinder inside a strong casing. The hollow channel running through the center is carefully shaped because the propellant burns from the inside out along the surface of this channel. By controlling the shape of the channel, engineers can control the burn rate and thrust over time. A star-shaped channel, for instance, provides high initial thrust because there is lots of burning surface area. As the star points burn away, the surface area decreases and thrust diminishes. Other shapes provide different thrust profiles. Some are designed to maintain constant thrust. Others ramp up or down. The art of solid rocket design lies in shaping the grain to produce exactly the thrust profile the mission requires. Once ignited by a pyrotechnic device, solid propellant burns vigorously, producing hot gases that exit through the nozzle just as in a liquid engine. But unlike a liquid engine, a solid rocket cannot be throttled or shut down. Once it starts, it burns until all the propellant is consumed. This lack of control is acceptable for boosters that operate for a fixed duration, like the solid rocket boosters on the Space Shuttle or many military missiles. The simplicity and reliability of solid rockets make them attractive despite their inflexibility. The solid rocket boosters on the Space Shuttle were among the largest ever built. Each booster was 45 meters long and 3.7 meters in diameter, generating 3.3 million pounds of thrust. They burned for about 2 minutes, providing most of the thrust during the initial ascent before separating and parachuting into the ocean for recovery and reuse. The propellant was a mixture of ammonium perchlorate, the oxidizer, aluminum powder, the fuel, and a rubbery binder to hold it together. When ignited, this mixture burned with a brilliant white flame and produced a distinctive rumbling roar that could be felt in the chest from kilometers away. The choice between liquid and solid rockets involves trade-offs. Liquid engines offer control, efficiency, and the ability to test fire before launch. Solid rockets offer simplicity, reliability, and the ability to store the fueled motor for long periods without maintenance. Modern launch vehicles often use both, with solid boosters for the initial push and liquid engines for sustained thrust and precise control. There are also monopropellant engines, which use a single substance that decomposes energetically when passed over a catalyst. Hydrazine is the most common monopropellant. When hydrazine encounters a catalyst, like iridium, it breaks down into nitrogen, hydrogen, and ammonia, releasing heat and producing gas. This decomposition requires no combustion, no oxidizer, no flame. The system is remarkably simple: a tank of hydrazine, a catalyst bed, and a nozzle. Monopropellant thrusters are widely used on satellites for attitude control and small orbit adjustments. They are reliable, restartable thousands of times, and relatively easy to implement. The efficiency of a rocket engine is measured by a quantity called specific impulse, often abbreviated as ISP. Specific impulse is the total impulse, thrust multiplied by time, per unit weight of propellant consumed. Think of it as the gas mileage of rocket engines. The higher the specific impulse, the more velocity change you can get from a given amount of propellant. Solid rocket motors typically have specific impulses between 250 and 300 seconds. Liquid kerosene-oxygen engines reach 300 to 350 seconds. Liquid hydrogen-oxygen engines can achieve 420 to 450 seconds. These numbers might seem abstract, but they have profound implications for mission design. An engine with twice the specific impulse can achieve the same mission with half the propellant, which means more room for payload or less initial mass to launch. The theoretical maximum specific impulse for chemical rockets is limited by the energy content of the chemical bonds being broken and formed during combustion. No chemical rocket can exceed about 500 seconds specific impulse in vacuum. This fundamental limit arises from chemistry itself, from the quantum mechanics of molecular bonds. To go beyond this limit requires different physics, electric propulsion, nuclear thermal rockets, or more exotic technologies. Now, you might wonder why spacecraft need such powerful engines at all. Why can't they simply drift gently into space? The answer lies in Earth's gravity. Our planet pulls everything toward its center with a force that depends on mass and distance. To leave Earth and travel into space, a spacecraft must overcome this gravitational pull. This requires reaching what is called escape velocity. Gravity is perhaps the most familiar yet mysterious force in nature. We experience it every moment of our lives, yet even today, scientists debate its deepest nature. For our purposes, we can understand gravity as an attractive force between any two objects with mass. The more massive an object, the stronger its gravitational pull. The closer you are to an object, the stronger you feel its gravity. Earth's gravity at the surface creates what we call 1g of acceleration, about 9.8 meters per second squared. This means that if you drop something, it accelerates downward, getting faster by about 9.8 meters per second every second. After 1 second, it is moving at 9.8 meters per second. After 2 seconds, 19.6 meters per second. The acceleration continues until air resistance balances gravity. But gravity weakens with distance, according to a precise mathematical relationship called the inverse square law. If you double your distance from Earth's center, gravity becomes 1/4 as strong. Triple the distance, and gravity becomes 1/9 as strong. This means that gravity never truly reaches zero. It just becomes weaker and weaker as you move farther away. Even at the distance of the Moon, Earth's gravity is still pulling, though much more gently than at the surface. Escape velocity is the speed an object needs to break free from a planet's gravitational influence and coast away indefinitely. For Earth, this speed is about 11.2 kilometers per second, or roughly 40,000 kilometers per hour. This is extraordinarily fast. Imagine traveling from New York to Los Angeles in less than 7 minutes. An object moving at escape velocity has enough kinetic energy to overcome Earth's gravitational potential energy all the way to infinity. You might think that to escape Earth, you need to maintain escape velocity all the way to space. But this is not true. You only need to reach escape velocity momentarily. Once you have that speed, even if your engines shut off immediately, you will coast away from Earth forever, gradually slowing down, but never stopping completely. Your kinetic energy continuously converts to potential energy as you climb out of Earth's gravitational well, but the total energy remains positive, meaning you will never fall back. Getting a spacecraft up to this speed requires enormous amounts of energy, which is why launch vehicles are so large and powerful. The vast majority of a rocket's mass at launch is fuel, sometimes accounting for 90% or more of the total weight. Consider the Space Shuttle, which weighed about 2,000 metric tons at liftoff. Of this, only about 78 metric tons was the orbiter itself, and only about 24 metric tons was payload. Everything else was fuel and tanks and rocket engines that would be discarded or jettisoned during ascent. The energy requirement comes from the combination of height and speed needed. A spacecraft in low Earth orbit is only about 400 kilometers above the surface, a tiny fraction of Earth's 6,371 kilometer radius. The extra altitude contributes relatively little to the energy requirement. What really matters is speed. At orbital altitude, a spacecraft must be moving at about 7.8 kilometers per second to avoid falling back. Most of the rocket's energy goes into achieving this horizontal velocity, not into gaining altitude. This might seem strange. If you want to go up, why do you need to go sideways so fast? The answer lies in what an orbit actually is. An orbit is not a stationary position in space. It is continuous freefall around the planet. The spacecraft is constantly falling toward Earth, but it is also moving sideways so fast that it keeps missing. The planet's surface curves away beneath the spacecraft at the same rate the spacecraft falls toward it. Imagine a very tall mountain, so tall it reaches above the atmosphere. From the top of this mountain, you throw a ball horizontally. The ball curves downward and hits the ground some distance away. Now throw it harder. It travels farther before hitting the ground. Throw it even harder, and it goes even farther. Eventually, if you could throw it fast enough, the ball would fall toward Earth, but the surface would curve away at the same rate. The ball would never hit the ground. It would circle the entire planet and come back to your mountain. It would be in orbit. This thought experiment was actually described by Isaac Newton in his book Principia Mathematica. He imagined a cannon on a very high mountain, firing cannonballs horizontally with increasing velocity. Below a certain speed, the cannonballs follow elliptical trajectories that intersect the Earth's surface. At exactly orbital velocity, the cannonball's trajectory matches Earth's curvature, and it orbits indefinitely. Above orbital velocity but below escape velocity, the orbit becomes an elongated ellipse extending farther from Earth. At exactly escape velocity, the trajectory becomes a parabola extending to infinity. But achieving orbital velocity is complicated by Earth's atmosphere. The atmosphere extends hundreds of kilometers above the surface, though it becomes increasingly tenuous with altitude. At low altitudes, air resistance is tremendous. An object moving at orbital velocity near the surface would experience such intense friction that it would burn up almost instantly. This is what happens to meteors and why returning spacecraft need heat shields. A rocket launching into orbit must thread a careful path. It cannot simply go straight up, because then it would have altitude but not the horizontal velocity needed for orbit. It cannot fly horizontally at low altitude because air resistance would be overwhelming. Instead, it follows a gradually curving trajectory, starting nearly vertical to quickly get above the dense lower atmosphere, then gradually tilting over toward horizontal as it climbs. By the time the rocket reaches orbital altitude, it is traveling nearly horizontally at orbital velocity. This curving path is called a gravity turn, and it is one of the most elegant maneuvers in spaceflight. Shortly after liftoff, the rocket begins to tilt slightly. Gravity and the aerodynamic forces on the rocket naturally cause it to continue arcing over in a smooth curve. The rocket's engines keep thrusting in the direction the rocket is pointing, which is increasingly horizontal. By the time significant speed is achieved, the rocket is above most of the atmosphere, so air resistance is negligible. The final result is orbital velocity in the desired direction at the desired altitude. Different orbital altitudes have different characteristics. Low Earth orbit, between about 200 and 2,000 kilometers altitude, is where most satellites and the International Space Station reside. Objects here complete an orbit every 90 to 127 minutes. They experience about 90% of Earth's surface gravity, but they are in constant freefall, so everything aboard feels weightless. The atmosphere extends even to these altitudes, extremely thin, but not quite zero. Over time, atmospheric drag causes satellites in low Earth orbit to gradually lose altitude and eventually re-enter the atmosphere. Medium Earth orbit, at altitudes of about 2,000 to 35,000 kilometers, is less commonly used. Some navigation satellites, including those of the Global Positioning System, orbit here. At these altitudes, satellites complete an orbit every few hours and experience much weaker atmospheric drag. They can remain in orbit for centuries without propulsion. Geostationary orbit is a special case at about 35,786 kilometers altitude, directly above the equator. A satellite here has an orbital period of exactly 24 hours, the same as Earth's rotation. This means the satellite appears to hover over one spot on the Earth's surface. This is tremendously useful for communications satellites and weather satellites, which can maintain continuous contact with a fixed area. Many satellites operate in geostationary orbit, forming a ring of spacecraft around the Earth's equator. Each orbit requires a specific velocity. To move from one orbit to another, a spacecraft must change its velocity, which means firing engines. To move to a higher orbit, the spacecraft fires its engines in the direction it is traveling, increasing its speed. This might seem counterintuitive. To go higher, you speed up? But yes, adding speed at one point in an orbit raises the opposite side of the orbit. The orbit becomes elliptical, with a high point called apogee and a low point called perigee. If the spacecraft fires its engines at perigee, the low point, it raises apogee, the high point. At the new higher apogee, the spacecraft fires its engines again to circularize the orbit at the higher altitude. This two-burn maneuver, called a Hohmann transfer, is the most fuel-efficient way to change between circular orbits. The first burn at the lower orbit raises the far side of the orbit. The spacecraft then coasts along this elliptical transfer orbit until it reaches apogee. The second burn at apogee raises perigee to match apogee, circularizing the orbit at the higher altitude. Moving to a lower orbit works in reverse. The spacecraft fires its engines backward, against its direction of travel, slowing down. This lowers the opposite side of the orbit. At the new lower point, it fires backward again to circularize at the lower altitude. Lowering an orbit actually requires adding speed at certain points, just as raising an orbit does, because you must first slow down to drop the far side of your orbit, then speed up at the lower altitude to avoid falling even farther. These maneuvers might seem simple, but they require careful planning and precise execution. Space agencies use sophisticated computer programs to calculate the exact timing, direction, and duration of each engine burn. Even small errors can have significant consequences, potentially causing a spacecraft to miss its target by thousands of kilometers. When the Mars Climate Orbiter arrived at Mars in 1999, A navigation error caused it to enter the atmosphere too low, and it was destroyed. The error? One team was using metric units, while another used English units, leading to a miscalculation in the thruster firings. But once a spacecraft reaches space and achieves the necessary velocity, something remarkable happens. It no longer needs continuous thrust to keep moving. This is because of another principle discovered by Newton. An object in motion tends to stay in motion unless acted upon by an external force. This is called inertia. In space, where there is virtually no air resistance and only weak gravitational influences from distant objects, a spacecraft can coast for years without using any fuel at all. It simply continues moving in the direction it was going, at the speed it achieved, until something changes its path or velocity. This principle of inertia makes long-distance space travel possible. A spacecraft might fire its engines for just a few minutes during launch, and a few more times for course corrections, but spend months or years traveling through space without any propulsion. The famous Voyager spacecraft, launched in the 1970s, fired their main engines for only a brief period, but have traveled billions of miles and are now beyond our solar system, still coasting through interstellar space. Let us pause and truly appreciate how strange and wonderful this is. On Earth, we never experience pure inertia. Everything we move eventually stops. A car runs out of momentum and rolls to a halt because of friction with the road and air resistance. A ball thrown through the air slows down and falls because of air resistance and gravity. A hockey puck sliding on ice eventually stops because even ice provides some friction. We are so accustomed to things naturally stopping that we intuitively feel motion requires continuous effort. But this is an artifact of Earth's environment, not a fundamental property of motion. In the vacuum of space, friction effectively disappears. There is no air to push against the spacecraft, no surface rubbing against anything. The spacecraft maintains its velocity effortlessly, indefinitely. Voyager 1, launched in September 1977, has been coasting for nearly 50 years. Its velocity relative to the Sun is about 17 kilometers per second, and it maintains this speed with no engine firings, no propulsion, nothing but its initial impulse and subsequent gravity assists still carrying it forward. The spacecraft will continue coasting through interstellar space for thousands, perhaps millions of years. Eventually, countless millions of years in the future, it might pass near another star. Unless it encounters something, unless gravity from some object deflects it or it collides with interstellar matter, it will continue moving in essentially the same direction at essentially the same speed forever. This is inertia made manifest, motion without end. Of course, gravity does influence spacecraft even when they are not firing engines. As a spacecraft travels through the solar system, it feels the gravitational pull of the Sun and planets. These gravitational forces constantly change the spacecraft's trajectory, bending its path into curves and ellipses. A spacecraft traveling from Earth to Mars is not traveling in a straight line, but along a curved path determined by the Sun's gravity. This is orbital mechanics, the mathematics of motion under gravitational influence. Understanding orbital mechanics was crucial for space exploration. Before computers, trajectories were calculated by hand using complex mathematical equations. Engineers would spend weeks calculating a single trajectory, checking and rechecking their work, because any error could doom the mission. Today, computers can calculate thousands of possible trajectories in seconds, allowing mission planners to optimize paths for fuel efficiency, flight time, or other criteria. Each journey through space has a launch window, a period during which the destination is in the right position for an efficient trajectory. For Mars missions, these windows occur roughly every 26 months, when Earth and Mars are properly aligned. Miss the window, and you must wait for the next one. This is why Mars missions tend to launch in clusters. In 2020, 3 missions launched toward Mars: NASA's Perseverance rover, China's Tianwen-1 orbiter and rover, and the United Arab Emirates Hope orbiter. They all launched within days of each other because they all needed to use the same launch window. The flight time from Earth to Mars typically ranges from 6 to 9 months, depending on the specific trajectory chosen. During this time, the spacecraft is mostly coasting, with perhaps a few mid-course correction burns to fine-tune the trajectory. These corrections are small, maybe changing velocity by a few meters per second, but they are crucial for ensuring the spacecraft arrives at precisely the right place at the right time. When the spacecraft approaches Mars, it is traveling at tremendous speed relative to the planet, often tens of kilometers per second. To enter orbit, it must slow down significantly. This requires a large engine burn called orbit insertion. The timing must be perfect. The spacecraft approaches Mars on a hyperbolic trajectory that would carry it past the planet and back into solar orbit. At precisely the right moment, as the spacecraft passes behind Mars, the engines fire, slowing the spacecraft just enough that Mars's gravity captures it into an elliptical orbit. Too little thrust, and the spacecraft escapes. Too much thrust, and it might crash into the planet or enter an unworkably low orbit. These critical moments are times of intense concentration for mission control teams. Radio signals take several minutes to travel between Mars and Earth, so the spacecraft must execute the maneuver autonomously. Controllers on Earth can only watch and wait, seeing the results several minutes after they occur. When the Mars Reconnaissance Orbiter performed its orbit insertion burn in March 2006, the spacecraft fired its engines for 27 minutes, while controllers on Earth could only hope the commands had been correctly executed. The burn had to reduce the spacecraft's velocity by about 1 kilometer per second. When telemetry finally arrived showing success, there was great relief and celebration. In fact, the vastness of space and the speed of light create fascinating communication delays. Light and radio waves travel at 300,000 kilometers per second, the fastest speed possible in our universe. Yet even at this incredible velocity, crossing interplanetary distances takes significant time. A signal from Mars takes between 4 and 24 minutes to reach Earth, depending on where the two planets are in their orbits. When Mars and Earth are on the same side of the Sun, the distance might be as little as 55 million kilometers, giving a signal travel time of about 4 minutes. When they are on opposite sides of the Sun, the distance exceeds 400 million kilometers, and signals take over 20 minutes each way. This means that controlling a Mars rover is not like playing a video game with a remote controller. You cannot respond in real time to what you see. You send commands, then wait many minutes to see the results. If something goes wrong, you do not know about it until many minutes later, and your corrective commands take many more minutes to arrive. This is why Mars rovers must be semi-autonomous, able to detect hazards and make simple decisions on their own. The rover might be commanded to drive to a particular rock, but it must navigate obstacles by itself, because waiting for controllers on Earth to steer around each rock would be impossibly slow. For missions to the outer planets, the communication delays become even more pronounced. Jupiter is about 630 million to 930 million kilometers from Earth, depending on positions. Radio signals take 35 to 52 minutes to make the one-way trip. A command sent to a spacecraft at Jupiter will not be received for nearly an hour, and the spacecraft's response will not return for another hour. Conversations become very slow exchanges separated by hours. At Saturn, the delays stretch to over an hour each way. At Uranus, signals take 2.5 to 3 hours. Neptune is even farther, with light travel time of about 4 hours. And Voyager 1, now in interstellar space beyond the influence of the Sun's gravity, is so far away that signals take over 22 hours each way. A command sent today will not be received until tomorrow, and the response will not return until the day after. Yet even at this distance, even after nearly 50 years of travel, Voyager continues to send back data about the space between stars, and engineers on Earth continue to guide it using commands carefully planned days in advance. However, moving through space is not just about going fast in a straight line. Spacecraft also need to navigate, change direction, and sometimes slow down. This is where the elegance of orbital mechanics comes into play. Orbital mechanics is the mathematics that describes how objects move under the influence of gravity. It governs everything from the Moon's orbit around Earth to the paths of comets through the solar system. When a spacecraft orbits Earth or any other body, it is constantly falling toward that body, but it is also moving sideways, so fast that it keeps missing. Imagine throwing a ball horizontally. The ball moves forward while simultaneously falling downward due to gravity. If you could throw it fast enough, the ball would fall at the same rate that Earth's surface curves away beneath it. The ball would never hit the ground, it would be in orbit. This is essentially what a spacecraft does. It moves fast enough sideways that even though gravity is pulling it downward, it keeps circling around the planet. The speed required to maintain a stable orbit depends on altitude. Closer to Earth, gravity is stronger, so a spacecraft must move faster to avoid falling back down. At an altitude of just a few hundred kilometers, where the International Space Station orbits, spacecraft must travel at about 7.7 kilometers per second, or 17,000 miles per hour. At higher altitudes, the required speed is lower. Geostationary satellites, which orbit at about 36,000 kilometers above the equator, move at about 3 kilometers per second, but appear to hover over one spot on Earth because their orbital period matches Earth's rotation. Changing a spacecraft's orbit requires adding or subtracting velocity, which means firing engines. To move to a higher orbit, the spacecraft fires its engines in the direction it is traveling, increasing its speed. This causes the orbit to become elliptical, stretching out on the opposite side. At the highest point of this new elliptical orbit, the spacecraft fires its engines again to circularize the orbit at the new altitude. To move to a lower orbit, the process is reversed. The spacecraft fires its engines backward to slow down. These maneuvers might seem simple, but they require careful planning and precise execution. Space agencies use sophisticated computer programs to calculate the exact timing, direction, and duration of each engine burn. Even small errors can have significant consequences, potentially causing a spacecraft to miss its target by thousands of kilometers. For journeys between planets, the principles become even more interesting. Traveling from Earth to Mars, for example, is not a simple matter of pointing in the right direction and firing the engines. The planets are constantly moving in their orbits around the Sun, and both the spacecraft and its destination are under the Sun's gravitational influence. Mission planners must calculate a transfer orbit, a carefully designed path that takes advantage of the motions of both Earth and Mars. The most fuel-efficient path between two planets is called a Hohmann transfer orbit. This elliptical orbit touches the orbit of Earth at one end, and the orbit of Mars at the other. The spacecraft leaves Earth's orbit by firing its engines to increase speed, which raises the far end of its orbit to meet Mars's orbit. The spacecraft then coasts along this elliptical path until it encounters Mars, at which point it fires its engines again to match Mars's orbital speed and enter orbit around the planet. Imagine you are standing on a slowly rotating carousel. You want to throw a ball to someone standing on a faster carousel rotating nearby. You cannot simply throw the ball at where the person is now. By the time the ball arrives, they would have moved. You must throw the ball to where they will be when it gets there. This is the challenge of interplanetary travel. You must launch not toward where the planet is, but toward where it will be months later when your spacecraft arrives. The Hohmann transfer orbit was first described by German engineer Walter Hohmann in 1925, decades before spaceflight became practical. His mathematical work described the most efficient way to travel between any two circular orbits around the same body. The elegance of the Hohmann transfer lies in its simplicity. Two burns, one to begin the transfer and one to end it, with passive coasting in between. No continuous propulsion needed, just two carefully timed impulses. For Earth to Mars, a Hohmann transfer typically takes about 8 to 9 months. The spacecraft begins in Earth orbit, fires its engines to add about 3 kilometers per second of velocity, enters a long elliptical orbit around the Sun that reaches out to Mars's orbital distance, coasts for most of the journey, then fires its engines again when it reaches Mars to enter orbit around the red planet. The total velocity change required is about 5.5 to 6 kilometers per second, split between the departure burn and the arrival burn. The beauty of a Hohmann transfer is that it requires only two main engine burns, one to leave Earth and one to arrive at Mars. However, it also requires patience. The spacecraft must wait for the planets to be in the right positions relative to each other, which only happens about once every 2 years for the Earth-Mars system. The journey itself takes about 6 to 9 months. During this time, the spacecraft is primarily coasting, using minimal fuel, relying on the laws of physics and the Sun's gravity to guide it along its path. But the Hohmann transfer is not always the best choice. If you are willing to use more fuel, you can take faster trajectories. High-energy transfers use more powerful departure burns to achieve higher speeds, reducing transit time. The Mars Science Laboratory mission, which delivered the Curiosity rover to Mars in 2012, used a trajectory that took only about 8.5 months. Earlier missions, with less powerful launch vehicles, sometimes took longer, up to 9 months. There are also low-energy transfers that use even less fuel than a Hohmann transfer, but take much longer. These trajectories make use of subtle gravitational interactions between multiple bodies, following paths through what are called Lagrange points, special locations where the gravitational forces of two large bodies balance. The Japanese Hiiten spacecraft, launched in 1990, used such a low-energy transfer to reach the Moon, taking many months but using very little propellant. These trajectories are mathematically beautiful, but require extremely precise navigation and a great deal of patience. When traveling to the outer planets, simple Hohmann transfers become impractical because the distances are so vast, and the velocity changes required are enormous. Jupiter is 5 times farther from the Sun than Earth. Saturn is nearly 10 times farther. The propellant needed for a direct Hohmann transfer to Saturn would be impossibly large. This is where gravity assists become not just useful, but essential. But there is an even more elegant way to travel through the solar system, one that uses almost no fuel at all. It is called a gravity assist, or gravitational slingshot. This technique uses the gravity of planets and moons to change a spacecraft's speed and direction without burning any fuel. It sounds almost magical, but it is based on straightforward physics. Here is how it works. As a spacecraft approaches a planet, it falls into that planet's gravitational field and begins to accelerate. From the planet's perspective, the spacecraft approaches, swings around, and leaves at the same speed it arrived. However, from the Sun's perspective, something remarkable has happened. The planet itself is moving through space in its orbit around the Sun. When the spacecraft swings past the planet in the direction the planet is traveling, it picks up some of the planet's orbital momentum. The spacecraft's speed relative to the Sun increases, even though its speed relative to the planet remains unchanged. Think of it like a baseball being hit by a moving bat. If you throw a ball at a stationary bat, it bounces back at roughly the same speed you threw it. But if you throw the ball at a bat that is swinging toward you, the ball bounces back much faster because it gains speed from the bat's motion. Similarly, when a spacecraft passes behind a planet in the planet's orbit, it gains speed from the planet's motion around the Sun. Let us explore this more deeply, because it truly is one of the most elegant techniques in spaceflight. Imagine you are on a skateboard, coasting slowly across a parking lot. A friend is driving by in a car at moderate speed. As the car passes, you grab onto its side mirror briefly, and the car pulls you along, increasing your speed to match the car's before you let go. You have gained speed without expending any of your own energy. You borrowed it from the car. A gravity assist works similarly, except instead of physically grabbing onto the planet, the spacecraft uses gravity. The spacecraft approaches the planet from behind, falling into its gravitational field. As it falls toward the planet, it accelerates, swinging around behind the planet. The planet's gravity pulls the spacecraft along in the direction the planet is moving. When the spacecraft slings around the planet and escapes from the gravitational field on the other side, it retains much of the velocity it gained. The result is that the spacecraft's velocity relative to the Sun has increased significantly. The amount of speed gained depends on several factors: the mass of the planet, how close the spacecraft passes, and the angle of approach. Massive planets like Jupiter can provide enormous speed boosts. The spacecraft Cassini, which explored Saturn, used gravity assists from Venus, Earth, and Jupiter to reach the outer solar system. Without these assists, it would have required far more fuel than it could possibly carry. Jupiter is particularly valuable for gravity assists because of its enormous mass and rapid orbital velocity. Jupiter has more mass than all the other planets combined. It orbits the Sun at about 13 kilometers per second. A well-executed gravity assist at Jupiter can increase a spacecraft's velocity by as much as 10 to 15 kilometers per second relative to the Sun. This is an astonishing amount of velocity gained, essentially for free, requiring no propellant, just careful trajectory planning. The Voyager missions provide perhaps the most famous example of gravity assists. Both Voyager 1 and Voyager 2 were launched in 1977 to take advantage of a rare alignment of the outer planets, an alignment that occurs only once every 175 years. The mission was called the Grand Tour, and it would allow a single spacecraft to visit Jupiter, Saturn, Uranus, and Neptune, using gravity assists at each planet to reach the next. Voyager 1 visited Jupiter in March 1979, taking stunning photographs and making important scientific measurements. Jupiter's gravity then accelerated the spacecraft towards Saturn, which it reached in November 1980. The trajectory was chosen to provide a close flyby of Saturn's large moon Titan, which unfortunately prevented Voyager 1 from continuing to Uranus and Neptune. but the scientific return from Titan was considered worth the trade-off. Voyager 2 followed a different trajectory that allowed it to continue beyond Saturn. It reached Jupiter in July 1979, then Saturn in August 1981, where it made close approaches to several moons. From Saturn, it continued to Uranus, arriving in January 1986. The gravity assist at Uranus sent it onward to Neptune, which it reached in August 1989, nearly 12 years after launch. At each encounter, the spacecraft's trajectory was carefully designed to provide the velocity change needed to reach the next planet, while also providing optimal conditions for scientific observations. The trajectory calculations were incredibly complex, involving the gravitational interactions of the Sun, the planets, and their moons. Computers were used, but they were far less powerful than a modern smartphone. Mission planners spent years calculating and refining the trajectories. The gravity assist at Jupiter increased Voyager 2's velocity by about 16 kilometers per second. The assist at Saturn added another 15 kilometers per second. By the time Voyager 2 left Neptune, it was traveling fast enough relative to the Sun to escape the solar system entirely. Today, both Voyager spacecraft are in interstellar space, still moving away from the Sun at about 17 kilometers per second, speeds they achieved primarily through gravity assists rather than rocket propulsion. Gravity assists can also be used to slow down a spacecraft. If the spacecraft passes in front of a planet in its orbit rather than behind it, the planet's gravity pulls back on the spacecraft, reducing its speed relative to the Sun. This technique was used by the Messenger spacecraft to slow itself down enough to enter orbit around Mercury, the closest planet to the Sun. Mercury presents unique challenges. It orbits very close to the Sun, where solar gravity is strong. To enter orbit around Mercury, a spacecraft must shed a tremendous amount of velocity. A direct Hohmann transfer from Earth to Mercury orbit would require more fuel than any practical spacecraft could carry. Messenger solved this problem with a series of gravity assists. Launched in August 2004, Messenger flew by Earth once, Venus twice, and Mercury 3 times before finally entering orbit around Mercury in March 2011. Each flyby was carefully designed to reduce the spacecraft's velocity step by step. The first Venus flyby in October 2006 reduced velocity by about 2.5 kilometers per second. The second Venus flyby in June 2007 reduced it by another 3 kilometers per second. The 3 Mercury flybys in January 2008, October 2008, and September 2009 provided additional velocity reductions and allowed the spacecraft to study Mercury during close approach. By the time Messenger was ready for orbit insertion, its velocity had been reduced so much that the final engine burn required relatively little propellant. The mission took nearly 7 years from launch to orbit insertion. But it succeeded in placing a spacecraft in orbit around Mercury using far less fuel than a direct transfer would have required. The mission demonstrated that with patience and clever trajectory design, even destinations that seem impossibly difficult can be reached. Planning a trajectory with multiple gravity assists is enormously complex. Mission designers use powerful computers to search through millions of possible paths, looking for trajectories that provide the necessary speed changes at the right times. The constraints are severe. The spacecraft must arrive at each planet at exactly the right time and place. The approach must be at the correct angle and distance to provide the desired velocity change. The trajectory must also satisfy the mission's scientific objectives, providing good viewing geometry for the instruments. Small errors in any gravity assist can have large effects downstream. If the spacecraft approaches a planet just a few hundred kilometers too high or too low, the velocity change will be different than planned. This error will cause the spacecraft to arrive at the next destination at the wrong time or in the wrong place, potentially missing the planet entirely. To prevent this, spacecraft routinely perform trajectory correction maneuvers, small engine burns that fine-tune the path between planets. These corrections are tiny compared to the gravity assists themselves, typically changing velocity by just a few meters per second. But they ensure that the spacecraft arrives at each planet precisely on target. The Cassini mission to Saturn used one of the most complex gravity assist trajectories ever flown. Launched in October 1997, Cassini could not fly directly to Saturn because the spacecraft was too massive and Saturn was too far. Instead, it flew by Venus twice, then Earth, then Jupiter, finally reaching Saturn in July 2004, nearly 7 years after launch. The trajectory was called VVEJ, Venus, Venus, Earth, Jupiter. The first Venus flyby in April 1998 increased Cassini's velocity and bent its orbit inward toward a second Venus encounter. The second Venus flyby in June 1999 provided another boost. The Earth flyby in August 1999 added more speed. Finally, the Jupiter flyby in December 2000 provided the final push, accelerating Cassini to about 47 kilometers per second relative to the Sun, fast enough to reach Saturn. Each flyby was also a scientific opportunity. Instruments were tested and calibrated. Observations were made of Venus, Earth, the Moon, and Jupiter. The Jupiter flyby was particularly productive, with Cassini observing Jupiter's atmosphere, moons, and magnetosphere in coordination with NASA's Galileo spacecraft, which was then orbiting Jupiter. The two spacecraft provided simultaneous observations from different angles, offering unique scientific insights. When Cassini finally arrived at Saturn, it performed one more type of gravity assist. Instead of swinging by Saturn itself, it made a close approach to Saturn's large moon Titan. Titan's gravity slowed the spacecraft just enough to be captured into orbit around Saturn. Over the following 13 years, Cassini performed over 100 flybys of Titan, each one slightly adjusting the spacecraft's orbit around Saturn. These repeated gravity assists allowed Cassini to explore Saturn's system in incredible detail, visiting dozens of moons and studying the planet's rings from many different angles, all without using much propellant. While chemical rockets have taken us to the moon and throughout the solar system, they have limitations. They are powerful but inefficient. They must carry enormous amounts of fuel, and once that fuel is burned, it is gone. For missions to the outer solar system and beyond, scientists have developed a different type of propulsion: ion engines, also called electric propulsion. Ion engines work on a completely different principle than chemical rockets. Instead of burning fuel to create hot gas, they use electricity to accelerate charged particles to very high speeds. The process begins with a propellant, usually a gas called xenon. Xenon atoms are electrically neutral, but when they're exposed to a beam of electrons, some of them lose an electron and become positively charged ions. These ions are then accelerated by an electric field, similar to how static electricity can make your hair stand up. The electric field pushes the ions through a grid at the back of the engine, expelling them into space at speeds of 30 to 50 kilometers per second, much faster than the exhaust from a chemical rocket. As the ions shoot out, they create thrust, pushing the spacecraft forward. The amount of thrust produced by an ion engine is tiny compared to a chemical rocket. If you were to place an ion engine on a scale on Earth, it would produce about the same force as the weight of a single sheet of paper. This might seem useless, but there is a crucial difference. An ion engine can run continuously for months or even years. Over time, these tiny pushes add up to enormous changes in velocity. The Deep Space One spacecraft, launched in 1998, was the first mission to use an ion engine as its primary propulsion. Its engine produced just 92 thousandths of a newton of thrust, but it ran for more than 16,000 hours, allowing the spacecraft to change its velocity by over 4 kilometers per second. This would have required many times more fuel with a chemical rocket. Ion engines are particularly useful for missions that require large changes in velocity, but have years to accomplish them. The Dawn spacecraft, launched in 2007, used ion propulsion to become the first spacecraft to orbit two different objects in the asteroid belt, the protoplanet Vesta and the dwarf planet Ceres. Its 3 ion engines allowed it to maneuver in ways that would have been impossible with chemical propulsion alone. The power for an ion engine comes from solar panels or nuclear generators. The engine itself consumes very little propellant. What it needs most is electricity. This makes ion engines incredibly efficient in terms of propellant usage. They achieve what is called high specific impulse, a measure of how effectively an engine uses its propellant. While chemical rockets have specific impulses of 300 to 450 seconds, ion engines can reach 2,000 to 5,000 seconds or more. The trade-off is time. Ion engines cannot produce enough thrust to launch from Earth or to make rapid maneuvers. They work best in the vacuum of space, where they can gently push a spacecraft over long periods. For missions to the outer solar system or for moving satellites between orbits, this gentle, patient approach is perfect. There are other types of electric propulsion as well. Hall effect thrusters are similar to ion engines, but use a different mechanism to ionize and accelerate the propellant. They are used on many communications satellites for maintaining their orbits. There are also more exotic concepts being researched, such as magnetoplasma dynamic thrusters and nuclear electric propulsion, which could eventually enable even faster travel to distant destinations. Now, let us consider how spacecraft know where they are and where they are going. Navigation in space is a delicate art that combines sophisticated sensors, careful calculations, and precise control. On Earth, we can use landmarks, compasses, and GPS to find our way. In space, there are no landmarks in the usual sense, and GPS satellites only work near Earth. So how does a spacecraft traveling through the solar system determine its position and orientation? The answer involves a combination of techniques. For determining position, spacecraft use radio communication with Earth. By measuring the time it takes for radio signals to travel between the spacecraft and ground stations, mission controllers can calculate the spacecraft's distance very precisely. Radio waves travel at the speed of light, so even with the vast distances involved, the technique works well. The Doppler shift in the radio signal, similar to how a siren's pitch changes as an ambulance passes, reveals the spacecraft's velocity relative to Earth. For missions near Earth, spacecraft can also use GPS signals to determine their position. Beyond Earth orbit, spacecraft must rely on other methods. Some use optical navigation, taking pictures of planets, moons, or asteroids, and comparing their positions to known star positions. This allows the spacecraft to triangulate its location. Determining orientation, or attitude, requires different sensors. Many spacecraft use star trackers, sophisticated cameras that photograph the stars and compare the patterns they see to an internal star catalogue. By recognizing which stars are visible and where they appear in the camera's field of view, the spacecraft can determine exactly which direction it is pointing. Star patterns are like cosmic fingerprints. They are unique and unchanging over human timescales. Sun sensors detect the direction of the sun, providing another reference point. Magnetometers measure the direction of magnetic fields, which can be useful near Earth or other planets with magnetic fields. Gyroscopes measure rotational motion, detecting when the spacecraft is turning and how fast. These are the same devices used in smartphones and airplanes, but built to much higher specifications for the harsh environment of space. All of this sensor data is processed by onboard computers that constantly monitor the spacecraft's state and compare it to the desired state. If the spacecraft is pointing in the wrong direction or moving on an incorrect trajectory, the control system activates devices called actuators to make corrections. For changing orientation, spacecraft commonly use reaction wheels. These are heavy spinning disks mounted inside the spacecraft. By changing the speed of these wheels, the spacecraft can rotate itself without using any propellant. This might seem like magic, but it is again a consequence of the conservation of angular momentum. When a reaction wheel inside the spacecraft speeds up, the spacecraft itself must rotate in the opposite direction to keep the total angular momentum constant. Imagine sitting on a swivel chair holding a spinning bicycle wheel. If you flip the wheel over, you and the chair will start to rotate in the opposite direction. Reaction wheels work on this same principle. A spacecraft might have 3 or 4 reaction wheels mounted along different axes, allowing it to rotate in any direction. The Hubble Space Telescope uses reaction wheels to point its instruments at distant galaxies with incredible precision, holding steady to within tiny fractions of a degree. However, reaction wheels have a limitation. Over time, as they change the spacecraft's orientation, they spin faster and faster until they reach their maximum speed. At this point, they become saturated and cannot provide any more control. To desaturate the wheels, the spacecraft must use small rocket thrusters to transfer angular momentum back out of the wheels into the spacecraft's rotation. Then, use the thrusters again to stop that rotation. This allows the wheels to be slowed down and reset. Some spacecraft also use control moment gyroscopes, which are more complex but more powerful than reaction wheels. These contain spinning rotors mounted on gimbals that can tilt. By tilting the gyroscope, the spacecraft experiences a torque that changes its orientation. The International Space Station uses control moment gyroscopes to maintain its attitude and orientation without constantly firing thrusters. For smaller adjustments, or when reaction wheels cannot be used, spacecraft use small rocket thrusters. These are typically much less powerful than the main engines and use different propellants. Some use hydrazine, a toxic but effective fuel that can decompose in the presence of a catalyst, producing hot gas without requiring an oxidizer. Others use cold gas thrusters that simply release pressurized gas through a nozzle. These thrusters provide quick bursts of force in specific directions, allowing the spacecraft to nudge itself into the correct position or orientation. Temperature control is another critical aspect of spacecraft operation that people rarely consider. Space is not uniformly cold. It is a place of extremes. In direct sunlight, surfaces can heat up to over 100 degrees Celsius. In shadow, temperatures can plummet to -100 degrees Celsius or lower. Electronic components, batteries, and instruments all have specific temperature ranges within which they must operate. Too hot, and they can overheat and fail. Too cold, and they can freeze or become inefficient. To manage these extremes, Spacecraft are equipped with thermal control systems. The simplest form of thermal control is passive, using materials that naturally absorb or reflect heat. Spacecraft are often wrapped in multi-layer insulation, a shiny blanket made of thin layers of reflective material separated by insulating layers. This insulation reflects sunlight away from the spacecraft and prevents heat from radiating away too quickly. Surfaces exposed to space are coated with special paints or tapes designed to have specific thermal properties. White or silver surfaces reflect sunlight and radiate heat efficiently, helping to keep the spacecraft cool. Black surfaces absorb heat, useful for warming specific areas. By carefully choosing where to place these coatings, engineers can balance the temperature across the spacecraft. For more active control, spacecraft use radiators, large flat panels that emit heat into space through thermal radiation. Since space is a vacuum, heat cannot be transferred through convection like it does in air. It can only be radiated away as infrared light. Radiators are designed to maximize this radiation, often positioned to face away from the sun and toward deep space. Heat pipes are elegant devices used to move heat from one part of a spacecraft to another without pumps or moving parts. A heat pipe is a sealed tube containing a small amount of liquid, often ammonia. At the hot end, the liquid evaporates, absorbing heat. The vapor travels to the cold end, where it condenses back into liquid, releasing the heat. Capillary action in a wick inside the pipe draws the liquid back to the hot end, completing the cycle. Heat pipes can transfer large amounts of heat efficiently and reliably, making them ideal for spacecraft. The International Space Station uses massive radiator panels to reject the heat generated by its systems and crew. These white panels, clearly visible on the station's exterior, can rotate to avoid direct sunlight while maximizing heat rejection to space. When the station is in shadow during Earth eclipses, additional heaters turn on to prevent critical systems from getting too cold. Some components require very specific temperatures. Scientific instruments might need to be kept near room temperature, while others, like infrared detectors, must be cooled to extremely low temperatures to function properly. Cooling systems using mechanical refrigerators or special coolers are used for these applications. The James Webb Space Telescope, for instance, operates at temperatures just a few degrees above absolute zero to detect the faint infrared light from distant galaxies. Power is the lifeblood of a spacecraft. Without power, none of the systems we have discussed can function. Most spacecraft near the Sun use solar panels to generate electricity. Solar panels are made of photovoltaic cells that convert sunlight directly into electrical current. These cells are usually made of silicon or other semiconductor materials. When light hits the cell, it knocks electrons loose, creating an electric current. The amount of power generated depends on the size of the solar panels, their efficiency, and how much sunlight they receive. Near Earth, solar panels can generate about 1 kilowatt of power per square meter of panel area. Farther from the Sun, the sunlight is weaker and less power is available. At Jupiter's distance, the sunlight is only about 4% as intense as at Earth, so spacecraft need much larger panels to generate the same amount of power. Solar panels must be able to rotate to follow the Sun as the spacecraft changes its orientation. They are mounted on movable booms that can be positioned for maximum sun exposure. The solar arrays on the International Space Station are enormous, spanning more than 70 meters from tip to tip, generating up to 100 kilowatts of power for the station's systems and experiments. For missions to the outer solar system, where sunlight is too weak to provide sufficient power, spacecraft use nuclear power sources. Radioisotope thermoelectric generators, or RTGs, use the heat produced by the natural radioactive decay of plutonium-238 to generate electricity. They contain no moving parts and can provide reliable power for decades. The Voyager spacecraft, Cassini, and the Mars rovers Curiosity and Perseverance all use RTGs. An RTG works by placing pellets of plutonium-238 inside a protective casing. As the plutonium decays, it produces heat. Thermocouples, devices that convert temperature differences into electricity, are placed between the hot radioactive core and the cold outer casing. This temperature difference generates a steady flow of electricity. The power output slowly decreases over time as the plutonium decays, but an RTG can continue producing useful power for many years. Space agencies have also considered larger nuclear reactors for spacecraft, particularly for missions that require very high power or for eventual human missions to Mars. A nuclear reactor would work similarly to those on Earth, using nuclear fission to generate heat, which would then be converted to electricity through various means. However, launching nuclear reactors into space raises safety concerns, and such systems are still largely in the research phase. Communication with spacecraft is perhaps the most remarkable feat of all. When a spacecraft is millions or billions of kilometers from Earth, how can we still send it commands and receive its data? The answer is radio waves, electromagnetic radiation that travels at the speed of light through the vacuum of space. Spacecraft are equipped with antennas that transmit and receive radio signals. These signals carry encoded information, commands from Earth telling the spacecraft what to do, and telemetry from the spacecraft reporting on its status and sending back scientific data. The spacecraft's antenna must be pointed toward Earth for communication to occur, which is why maintaining correct orientation is so important. The distances involved create challenges. Radio signals traveling at the speed of light still take time to cross space. A signal from Mars takes between 4 and 24 minutes to reach Earth, depending on where the two planets are in their orbits. Commands sent to Voyager 1, now beyond the edge of our solar system, take over 22 hours to arrive. Communication is not a conversation, but an exchange of carefully timed messages with long pauses in between. The signals also become very weak over distance. A spacecraft transmitter might send out only a few watts of power, less than a household light bulb. By the time that signal crosses hundreds of millions of kilometers, it is incredibly faint. To detect these weak signals, space agencies use enormous dish antennas on Earth. NASA's Deep Space Network consists of 3 large facilities located around the world, each with massive dish antennas up to 70 meters in diameter. These giant ears can detect signals so weak they would barely illuminate a grain of sand. The data sent back by spacecraft is precious. After traveling months or years to reach another world, a spacecraft might collect images, measurements, and observations that represent humanity's first close look at that place. This data is carefully transmitted back to Earth, often at very low rates, due to the limited power available. A spacecraft at Mars might transmit data at only a few kilobits per second, much slower than even the earliest internet connections. Scientists must wait patiently as the images and data trickle in, line by line, pixel by pixel. As we have explored these various systems, you might notice a common thread. Spacecraft are designed with redundancy and reliability as top priorities. Space is an unforgiving environment. There is no way to send a repair crew to fix a problem, so everything must work correctly the first time and continue working for years or even decades. Engineers build spacecraft with backup systems for critical components. If one computer fails, another takes over. If one reaction wheel stops working, others can compensate. Spacecraft carry extra fuel, additional batteries, and redundant radio transmitters. They are tested extensively on Earth, subjected to vibrations that simulate launch, placed in vacuum chambers that mimic space, and heated and cooled through temperature extremes to ensure they will survive the actual mission. Despite all this care and preparation, spacecraft sometimes encounter unexpected problems. When the Galileo spacecraft was launched toward Jupiter, its main antenna failed to deploy properly. Engineers could not repair it, but they found creative ways to work around the problem, using the smaller backup antenna and advanced data compression to complete most of the mission's objectives. When the Hubble Space Telescope was first deployed, it was discovered that its main mirror had been ground to the wrong shape, causing blurry images. Astronauts later installed corrective optics during a repair mission, giving Hubble the crystal-clear vision it is famous for today. Looking toward the future, new propulsion technologies are being developed that could revolutionize space travel. Solar sails use the gentle pressure of sunlight to propel spacecraft without any fuel at all. A solar sail is a large, extremely thin reflective sheet, sometimes kilometers across. Photons from the sun carry momentum, and when they reflect off the sail, they transfer that momentum to the spacecraft. The force is incredibly small, but over months and years in space, a solar sail can achieve significant velocities. The Japanese spacecraft Icaros, launched in 2010, successfully demonstrated solar sail technology during a flyby of Venus. Future missions might use solar sails to explore the outer solar system, or to position satellites in unusual orbits that would be difficult or impossible to reach with conventional propulsion. Scientists are also developing more powerful forms of electric propulsion. Magnetoplasma-dynamic thrusters could provide higher thrust than current ion engines, while maintaining excellent efficiency. Fusion propulsion, using the same process that powers the Sun, could theoretically enable much faster travel to the outer planets and beyond, reducing trip times from years to months. However, these technologies are still in early research stages and face significant technical challenges. Laser propulsion is another intriguing concept. A powerful laser on Earth or in orbit could beam energy to a spacecraft, heating propellant or pushing a light sail. This would allow the spacecraft to carry less power generation equipment, reducing mass. However, keeping a laser focused on a spacecraft over millions of kilometers is an enormous technical challenge. For crewed missions to Mars and beyond, nuclear thermal propulsion is being reconsidered. This system would use a nuclear reactor to heat hydrogen propellant to extreme temperatures, expelling it through a nozzle for thrust. Nuclear thermal rockets could provide twice the specific impulse of the best chemical rockets, making long-distance crewed missions more feasible by reducing the amount of propellant needed. As we consider these future possibilities, it is worth reflecting on how far we have come. Less than 70 years ago, humans had not yet launched anything into space. The first artificial satellite, Sputnik, orbited Earth in 1957. Just 12 years later, humans walked on the Moon. Today, spacecraft have visited every planet in our solar system, landed on asteroids and comets, explored the atmospheres of other worlds, and sent back images of breathtaking beauty and scientific value. The Voyager spacecraft, launched in 1977, have now left the solar system entirely and entered interstellar space, carrying messages from Earth to any civilization that might someday find them. The Hubble Space Telescope has revealed galaxies billions of light-years away, showing us the universe as it was in its infancy. The Mars rovers have driven for kilometers across the red planet, analyzing rocks and soil, searching for signs of ancient water and possibly life. All of this has been accomplished through the careful application of physics, the patient work of engineers and scientists, and the elegant principles we have explored tonight. Spacecraft travel through space by throwing mass in one direction to move in the other. They navigate using starlight and radio waves. They maintain their temperature through careful design and the properties of materials. They generate power from sunlight or nuclear decay. They communicate across vast distances with faint radio whispers. Behind every spacecraft is a story of human curiosity and determination. Each mission represents thousands of people working together, solving problems, overcoming setbacks, and pushing the boundaries of what is possible. When you see an image from Mars or Saturn or the edge of the observable universe, you are seeing the result of this collective effort, this peaceful exploration of the cosmos. Space travel reminds us that we are part of something much larger than ourselves. The Earth, beautiful and fragile, is a tiny oasis in an enormous ocean of space. The spacecraft we send out are like messages in a bottle, carrying our instruments and our questions into the unknown. They extend our senses, allowing us to see and measure things we could never experience directly. As you prepare for sleep tonight, imagine those spacecraft still out there, silently coasting through the darkness. Voyager 1, now more than 23 billion kilometers from Earth, still sends back data about the space between the stars. The Parker Solar Probe dives closer to the Sun than any spacecraft before it, its heat shield glowing white-hot as it skims through the solar corona. The James Webb Space Telescope peers into the infrared universe, capturing photons that have been traveling for 13 billion years. These machines are extensions of us, exploring on our behalf, answering questions and raising new ones. They operate in an environment that would extinguish human life in moments, yet they continue their missions with patient persistence. They are testaments to human ingenuity and our deep desire to understand the universe we inhabit. The principles that govern spacecraft travel are the same principles that govern everything in the universe. Newton's laws, discovered hundreds of years ago, still accurately describe motion from the smallest particle to the largest galaxy. The conservation of momentum, the constancy of the speed of light, the geometry of space-time, these are not human inventions, but universal truths that we have merely discovered and learned to use. In learning how spacecraft travel, we learn about the nature of reality itself. We learn that space is not a void, but a fabric that can be warped by mass. We learn that time is not absolute, but depends on velocity and gravity. We learn that matter and energy are interchangeable, and that the universe operates according to laws that can be understood through careful observation and mathematics. This understanding brings with it a sense of connection. The same atoms that make up spacecraft and planets and stars also make up our bodies. The carbon in our cells was forged in the hearts of ancient stars that have long since vanished. The oxygen we breathe, the nitrogen in our DNA, the calcium in our bones, all of it was created in stellar furnaces or in the violent explosions of supernovae. We are, quite literally, made of stardust. And spacecraft are our way of returning to those stars to learn their secrets. There is something deeply peaceful about space travel when you think about it this way. The violence of a rocket launch, with its fire and thunder, gives way to the serene silence of orbital mechanics. A spacecraft glides through space with the grace of a planet or a moon, following paths dictated by gravity and momentum. There is no struggle, no friction, no resistance. Just the gentle, eternal dance of mass and motion. As you drift towards sleep, let your mind float like a spacecraft through the darkness. Feel yourself weightless, free from the pull of Earth, coasting through the quiet vastness. There are no sharp edges in space, only smooth curves and gradual accelerations. There is no up or down, only the gentle pull of gravity from distant suns. There is no noise, only the profound silence broken occasionally by the hiss of a thruster or the hum of an instrument. Your breathing slows, matching the patient pace of a spacecraft on a years-long journey. Your thoughts become like data packets, transmitted across vast distances, their urgency fading with distance until they are just faint signals in the darkness. Your body relaxes, no longer needing to fight gravity or maintain posture. You are floating now, suspended in that peaceful state between waking and sleep. The spacecraft continue their journeys, as they have for years and will for years to come. They do not hurry. They do not worry. They simply move forward, following the path set for them, trusting in the laws of physics that never fail. And you can trust in those same laws, in the reliability of natural processes, in the certainty that the universe follows rules that can be understood and predicted. There is comfort in this knowledge. The same forces that guide a spacecraft across billions of kilometers also keep our planet in its orbit, bring the seasons in their rhythm, and ensure that the sun will rise tomorrow as it has for billions of years. We live in a universe that, for all its vastness and mystery, operates according to principles that are stable and knowable. So rest now, knowing that while you sleep, spacecraft are traveling through the cosmos, gathering data, taking images, measuring magnetic fields and radiation, sending back their quiet reports to the patient humans who built them. Rest knowing that the universe is vast but not chaotic, mysterious but not incomprehensible, dark but filled with light from countless stars. Let the gentle principles of orbital mechanics lull you into peaceful dreams. Let the patient efficiency of ion engines remind you that great things can be accomplished with small, persistent efforts. Let the redundant systems of a spacecraft reassure you that there are always backups, always alternative paths, always ways to adapt when things do not go as planned. The spacecraft teach us patience. They teach us to think long-term, to plan carefully, to trust in the laws of nature. They teach us that vast distances can be crossed with time and persistence. They teach us that seemingly insurmountable challenges can be overcome with creativity and determination. They teach us to look up, to wonder, to question, to explore. And now, as your breathing deepens and your thoughts quiet, let yourself join those spacecraft in spirit. Let yourself glide through the peaceful darkness, free from worry, free from rush, free from the weight of the day. You have traveled far today in your own way, navigated your own challenges, overcome your own obstacles. Now it is time to rest, to recharge, like a spacecraft passing through the shadow of a planet, saving energy, preparing for the next phase of the journey. The stars will still be there when you wake. The spacecraft will still be traveling, still transmitting, still exploring. The universe will continue its ancient dance of gravity and light, and you will have rested, restored, ready to continue your own journey through this remarkable existence. Each spacecraft is a small miracle, a collection of metal and silicon and carefully arranged molecules that somehow knows how to navigate the cosmos. Each one carries with it the dreams and hopes of its creators, the accumulated knowledge of centuries of scientific inquiry, and the simple human desire to know what lies beyond the next horizon. They are our ambassadors to the universe, our way of reaching out beyond our small world to touch the infinite. As they coast through the darkness, following trajectories calculated with extraordinary precision, they remind us that we too are on a journey. Our planet is a spacecraft of sorts, carrying us through space at 30 kilometers per second as it orbits the Sun. We are all space travelers, whether we realize it or not, riding this beautiful blue world through the cosmic ocean. The spacecraft we build and launch are simply extensions of this journey, pushing a little farther, looking a little closer, asking new questions. They represent the best of what humanity can achieve when we work together toward a common goal, when we apply our intelligence and creativity to understanding rather than destroying, to exploring rather than conquering. You have done enough today. You have learned and grown and persevered. Now, close your eyes and let go. Let the gentle rhythms of the cosmos carry you into sleep. Let the silent glide of spacecraft through space guide you into dreams. Let the vast, patient universe hold you safely as you rest. The journey continues, but for now, you can simply float, weightless and peaceful, in the quiet space between day and tomorrow. Trust in the journey. Trust in the process. Trust in the fundamental laws that govern all motion, all energy, all existence. Sleep well, traveler. The stars are patient. The cosmos is vast, and you are exactly where you need to be. The spacecraft will keep exploring. The planets will keep turning. The galaxies will keep spinning, and you will rest, safe and sound, knowing that you are part of this grand cosmic story. Good night.